Okay, so this is a screencast for qualitative analysis. Okay, so broadly speaking, what is qualitative analysis? We want to make use of known reaction that has observable changes for us to identify unknowns. So in the case of qualitative analysis in your syllabus, there is identifying cations and anions. But as we progress on to say organic chemistry or redox, you'll realize that there are other tests that we can do that identify, say, what's a oxidizing or reducing agent, as well as the different organic chemistry groups. Okay, so let's start. What's cations and anions? A cation is a positively charged ion, and an anion is a negatively charged ion. So all sorts are ionic compounds. That is to say, they are made up of one plus and one minus, one cation and one anion. So generally, there are two ways we can make observable changes. One is we try to form a precipitate. So what is a precipitate? A precipitate is formed when two aqueous solution or a gas is added together to form a solid. And this solid will be the precipitate plus whatever. Okay. So an example, how this works is that in the solution, so say I have sodium chloride dissolved in water. I add silver nitrate to the solution. Now what happens is that these ions can freely move about in solution and they will collide with each other. So we know that when sodium collides with nitrate, nothing happens because sodium nitrate is a salt that's still soluble in water. So it remains dissolved in water and continues moving about, nothing much changed. But the interesting thing is when silver collides with chloride, because we know that this is an insoluble salt. So what happens is it will continue sticking together and it will continue gathering more silver and more chloride ions. So while sodium nitrate remains in water, silver chloride will form a precipitate, and we will see it as the solution turning cloudy and whatnot lah. Okay, so that's one. We can form a precipitate, which is a solid that's formed out of two aqueous solution adding together, or a gas being bubbled into a solution. So an example would be the lime water test. Okay, then that brings us to our second observable change, which is to evolve a gas. So how do we evolve a gas? Now, there are various reactions that we have learned before that produces a gas as a product. So one being an acid plus carbonate reaction. This gives us carbon dioxide. Another reaction that we know is acid plus metal. And we also learn alkali plus ammonium salt, right? That gives us ammonia. So there are a few reactions that we know that can evolve a gas, and we can then test for the gas to confirm the identity of the ion. So for example, if I have an acid carbonate reaction, I can test for carbon dioxide gas. If there is carbon dioxide evolved, I can work backwards and confirm that indeed what I added acid to is a carbonate. I can also, when I add an alkali, which is hydroxide, okay, I would then be able to identify that an ammonium ion is produced, it was in the original solution if ammonia gas is evolved. So how do we test for cations? Cations can be identified by adding aqueous sodium hydroxide and aqueous ammonia. Now why do we add these two? Is to give precipitates, and these precipitates are actually what we call your metal hydroxides. Now NaOH and aqueous ammonia. These are both alkalis. And recall what's an alkali? It dissolves in water to give hydroxide ions. Okay, so what happens is it provides these hydroxide ions that will collide with the metal cations to form a metal hydroxide. So if you recall the solubility table, most hydroxides are insoluble in water, except for a few. Okay, so except for hydrogen, your group 1, ammonium, it will tend to give a precipitate. Of course, we also have some that's slightly soluble. Your calcium hydroxide is slightly soluble in water, and barium hydroxide. Okay, so for your cations, you will see that all the precipitate forms are hydroxides. Now, this is not that big of a problem for your sodium hydroxide, but students are often confused as to what's the identity of the precipitate form when it's aqueous ammonia. So just note that it's also the hydroxide being formed. That's because ammonia is also an alkali. So if I were to write the equation, ammonia, when you add it to water, this is a reversible reaction that will form ammonium ions and hydroxide ions. And because it forms hydroxide ions, it is an alkali. Okay, you don't need to know this equation. This is just trying to explain to you why aqueous ammonia is an alkali. Okay, so over here you see that it's lead 2. This is the old syllabus. So the updated syllabus is actually aluminium. Okay, so instead of lead 2 hydroxide, it will be aluminium hydroxide. Same for here. So your lead 2, it is aluminium. So in the pure chem syllabus, you actually learn that lead 2 and aluminium, they have the same observations for both NaOH and NH3. So in this case, if they have the same observation, then what you have to do is you need to do one more step, which is to add potassium iodide. So the difference is lead 2 will form a yellow precipitate with iodide, because if you recall, lead 2 chloride is insoluble and lead 2 iodide is actually also insoluble. So lead 2 iodide will form a yellow precipitate, and it's a bright yellow precipitate, so it's very iconic, very easily identifiable. Whereas aluminum iodide, if you follow the solubility of chlorides, is actually soluble in water, so no precipitate will be formed. There are colored precipitates, like for your transition metal. Okay, then we have the not colored ones, which are all white. So then let's do this flowchart for the test for cations. I think I'll need you to add one more, which is there's no precipitate. If you heat it and there's no gas, this means that it is likely your group 1 ions. Okay. However, if you add sodium hydroxide, no precipitate, and you heat it, sorry, this one got moist, moist red litmus paper blue, and you get ammonia. This tells you that ammonium ion is present. This would be your alkali plus ammonium gives you salt water and ammonia gas. Okay, so this one just requires alkali and heat. Now, if it forms a precipitate, there's generally two categories, white color and colored. So how do we write this? If it is an insoluble precipitate, this is your calcium 2 plus. If it dissolves to give a colorless solution, that is zinc, as well as your aluminium or lead, depending on your syllabus. Okay, so this is the old syllabus. So if you do TYS, you will see questions involving lead 2 plus. This is the new syllabus. Okay, so if you do your 10-year series and you think the answer is aluminium, but the answer key right lead, actually you are still correct. Okay, so they have the same observation and hence your conclusion is the same. For colored precipitate, there's a few. If it is blue, it is Cu2 plus. If it is green, it is Fe2 plus. If it is dirty brown, if it's reddish brown, it is Fe3 plus. When we add aqueous ammonia and there's no precipitate form, this is likely your sodium, potassium. Ammonium, you can't really add aqueous ammonia to ammonium because adding aqueous ammonia to water definitely will give you ammonium ions. But we also know that calcium does not form a precipitate when we add aqueous ammonia. Then if it adds white precipitate, this will be your aluminium or lead. And if it dissolves, it is zinc 2 plus. So what I remember is that zinc dissolves in excess for both. Okay, but not the rest. Now notice that for these three, right, for your sodium one, these three ions here are your amphoteric oxides. So you remember this set of three before. They are the amphoteric oxides and they are also amphoteric hydroxides. So what it means is it can react with both acids and alkali, and that's why when I add excess alkali, right, it will dissolve in the alkali because it reacts with the alkali to dissolve to give another solution. You don't need to know what is the solution form because it's a complex ion. Just know that because it's amphoteric, it reacts with it. Now again here, if you form the three colored precipitates, if you add it in excess and it's insoluble, that will be your iron 2, iron 3. Dissolve to give a dark blue solution, that's your copper 2 plus. Okay, so this is how you can sort of memorize this set. We move to your anions. So for anions, you see that for nitrate, right? The test is to add sodium hydroxide, aluminium foil, and warm. The sodium hydroxide and warming part is the same as the test for ammonium. So take note of the difference. Test for ammonium is we add NaOH and warm. So the difference is actually this aluminium foil bit. So if you see the presence of aluminium foil, then you know it's a test for nitrate. And if you look at the observations, you can see that these two test for a gas, these two evolves a precipitate. Okay, so testing for gas, this nitrate one tests for ammonia gas, and carbonate, we mentioned, tests for carbon dioxide. So you need to know how to describe the test for the gas. First step is always to write the effervescence is observed. Second is to state the color and smell of the gas. And then the test, specific test for the gas. What are some keywords? For ammonia gas, you must say that the litmus paper is moist. color and smell of gas. So first, effervescence. Second, color and smell. Third is specific test for gas. Lastly, write the identity of the gas. Okay, so 1, here we should say a colorless, odorless gas. Okay, 2, this is the third one, white precipitate with lime water. 3, and lastly, identity of gas. Now, sometimes the questions will ask you, what is this white precipitate? To do that, you need to know what is lime water. Lime water is calcium hydroxide, aqueous. So what is the white precipitate form? Now let's write the equation. Calcium hydroxide, lime water. When carbon dioxide is bubbled into it, carbon dioxide is an acidic oxide, whereas lime water is an alkali. So this is actually a neutralization reaction to give us calcium carbonate and water. And we know that this is a solid, this is a gas, aqueous, liquid. So remember just now we said that precipitate is formed when it is a solid forming out of two aqueous solution or gas bubble into an aqueous solution. Yeah, so the white precipitate form is calcium carbonate. Okay, then we move on to chlorides and sulfates. So for the chlorides and sulfates, actually what we are doing here is to make use of their specific solubility rules. So if you remember, all chlorides are soluble except for silver chloride and lead 2 chloride. So therefore, when we add silver nitrate and it forms a precipitate, it is likely that a chloride is present. Now, of course, silver also can form other insoluble salts, Ag+. If I add it to chloride, I know it will form a precipitate. If I add it to carbonate, I also know it will form a precipitate. Reason being, carbonates are generally insoluble. So how do I make sure that if a precipitate form, it is definitely chloride and not carbonate? That's the dilute nitric acid part. Okay, the the presence of nitric acid is to get the H+, such that it will react away your carbonate. Okay, so any precipitate form must be due to the presence of chloride. Same for sulfate. It makes use of the specific solubility rules of sulfates, which is that barium, calcium, and lead 2 sulfate are insoluble in water. So that's why it adds barium nitrate. The dilute nitric acid is again to remove the carbonates. So barium 2 plus, it forms a precipitate with your sulfate, of course, but also carbonates. So the acid helps you to remove this carbonate and ensures that any precipitate form is caused of the presence of sulfate. Tests for gases, you have learned many of them before. You've learned hydrogen, carbon dioxide, and ammonia. So the new ones will be oxygen, chlorine, and sulfur. For oxygen, it makes use of a glowing spleen. So what does a glowing spleen looks like? If you, are Chinese and pray before, you have seen joss stick before and it glows red at the top, right? It's not that there's a flame there. It's just glowing red. So that's a glowing splint. So why will it relight or rekindle? That's because the presence of the high concentration of oxygen, which is necessary for fire, helps it to relight. Okay, so you will see from here, you will become like that. Flame. Okay. For chlorine gas, you'll see moist blue litmus paper will turn red and bleach. So what it will look like is this. At first holding blue, then it becomes a bit red when you hold it over, and then at the end it will become bleached. So you just see the color of the filter paper. For sulfur dioxide, it's the same. Okay, just at this time, the filter paper is soaked in potassium manganate 7. Okay, just note that this is KMNO4. So it is purple, but it will turn colorless. When it turns colorless, it actually becomes Mn2+. Okay, so it will be what we call reduced from 7 to 2. You will learn about the reduction in the next topic. Okay, so there's actually a whole list of colors of compounds and elements and whatnot, but don't have to worry too much. Okay, so if you look here, most metals are silver or gray, okay, except for copper, it is reddish brown. So copper is quite unique. You need to remember a lot of the copper colors. Copper 2+ is blue, but some of the solids you need to remember. Copper 2 carbonate, like to test, is a green solid. Copper 2 oxide is a black solid. Iron 2 salts are generally green. Okay, iron 3 salts are reddish brown. Okay, generally everything else is a white color. Those with colors you will see. Nickel and chromium are not, you don't really need to memorize that. What else? Oxidizing reducing agent, we'll cover this during redox. Yeah, so that's about it.